I just learned stands for fluide, automatique, et système thermique. So there's a rhyme there in the title. Anyway, I first became pretty closely acquainted with Neil's beautiful work on viscous jets and coiling, instability, and such. About 10 years ago, when I was working on Jackson Pollock's paintings, was an art historian first, and then with Mahadevan, and we discovered in some of Pollock's painting coiling instability, basically. And so I followed his work, and in particular, the ever-changing diagram of the sort of space of this instability, which got more and more complicated. So I had to update my talk frequently, but with pleasure. Neil got his undergraduate education from Yale. Then he moved to Columbia, where he was a research associate. Then in Chicago he got a PhD in 1981 before Columbia. Then he returned to Yale as a professor and stayed there pretty much to the end of last century. And then in 2000 he moved to France, first at CNRS, and then I think from 2008 or so in FAST. And I think previously he worked on various geophysical problems, but for some time on this problem with colleagues, including colleagues here in Cambridge, John Lister, and others. Anyway, today he will talk indeed about viscous and elastic threads, so let's welcome him.
Well, thank you very much for coming. I certainly appreciate your presence here. I want to thank, first of all, the Simons Fellowship Committee for their kind invitation, and acknowledge my collaborators, many of you whom you see listed here, quite a few from Cambridge. What I want to talk about today is a beautiful pattern forming system that arises out of one of the simplest experiments you can perform in fluid mechanics, where you simply let a thread of viscous fluid fall vertically onto a surface. And when we started working on this, we had no idea how complicated and rich the problem would become. And I hope I can convey a bit of that to you today. Now, how do I get rid of this little...
Just say later.
Say later. Well, I can't click on it with this.
No, you have to go to your machine.
Yes, I know. It doesn't appear.
Yeah, just put the pointer on the later.
Oh, I see. There we go. No.
Let's go.
Oh, okay, fine. It'll be. Well, let me start with a couple of applications of this. There are applications. Of course, the reason we did it is just for the fundamental interest and for the beauty of it. But it's worthwhile looking at a couple of applications. The first is the production of non-woven fabrics, which is about 30% of world textile production. It's done using a device like this, which is about 3 meters high. And in the middle of it, you have a piece from which thousands of thin viscous threads of molten polymer fall. They solidify as they fall. They fall onto a moving belt, which is here moving to the left. And they form a fabric which looks like this, with a completely random distribution of fibers. Another application that Andrej already mentioned is action painting, as practiced by Jackson Pollock. I recommend Andrej, the article by Andrej and collaborators in Physics Today, if you haven't seen it already. But this is a picture of Jackson Pollock dribbling thin viscous filaments onto his canvases, and you can see some of the coiling patterns if you look closely at the canvases that Jackson Pollock created. Okay, I want to start with the classic phenomenon of liquid rope coiling, and I'll let you look at this device, which many of you have seen already, but it displays the phenomenon quite nicely when you turn it over. So we approach this problem using a mixture of experiments, theory, and numerics. This shows the experimental setup that my colleagues at ENS and in Zanjan in Iran used. It's a very simple setup in which you have a syringe pump filled with the working fluid, activated by a stepper motor. You extrude a thin viscous filament from the bottom of the syringe pump. It falls onto a surface and you observe it with a rapid camera. Nothing more complicated than that. And on the right-hand side, you have a blow-up of the filament itself. I'll just indicate some of the parameters. You have a flow rate Q extruded through a nozzle of diameter D. The thread falls through a height H and coils with a frequency capital omega. The most important physical property of the fluid, of course, is the viscosity. And just for short, I'll call the long vertical part of the thread the tail, and the coiled part at the bottom the coil. R, by the way, is the radius of that coil, and A1 is the radius of the filament as it enters the coil region. So the movies work. I'm not sure about the others. This just shows different modes of coiling. As you see, this is a case with a very small length scale. This is for a larger fall height. And what you notice here is that each loop of the coiling filament is not directly on top of the preceding one. That will become important later on in the talk. This one is for a yet higher fall height, and now you see that the long tail of the viscous rope executes some quite large horizontal oscillations. We'll see the reason for that in shortly. And this is a more inertially dominated case where the fall height is still larger. And there you see that the upper part of the filament is largely straight, and the lateral motion of the filament is confined to the lower portion near the coil. Here's another movie showing multi-stable coiling. Here you see a well-defined frequency and coiling radius, but in a while it will seemingly get bored with what it's doing, and it changes direction and coils now with a larger radius and a lower frequency. And in fact, if you observe this for a long time, you see that it bounces back and forth between the two states. So let's now move towards the mathematical model that I'm going to discuss. The model can be best understood by considering the different forces that act on a coiling viscous rope or thread. Obviously, there's gravity. That's the driving force for coiling in most cases. There are surface tension forces. Those are of secondary importance. They're included in the numerical model I use for comparison with the experiments, but they don't lead to any really new physics. Then thirdly, there's the viscous resistance to deformation, and that viscous resistance is of three kinds. If I take, I hope I don't ruin anything here. If I take a viscous thread, I can deform that by stretching, I can deform it by bending, and I can deform it by twisting. Three different modes of deformation, and the viscosity resists all of those in slightly different proportions. You may have heard of Troughton viscosity, for example, for a stretching viscous thread. So we have the resistance to stretching, bending, and twisting, all of which have to be present in the equations. And finally, there is inertia. This shows the accelerations involved. Coiling now, to model mathematically, it's convenient to put yourself in the rotating reference frame, the co-rotating reference frame with the point of contact that describes a circle in the laboratory frame. And in that rotating frame, there's of course the intrinsic acceleration, which is just the advective rate of change of the direction of the fluid along the thread. And there are the usual Coriolis and centrifugal contributions due to the fact that you're in a rotating reference frame. So here, in a very shorthand way, is the mathematical formulation of the coiling problem. You have a total of 17 variables. This is a problem in which you take the three-dimensional Navier-Stokes equations, do an asymptotic expansion, and reduce them to equivalent equations for the axis of the thread. So the only spatial variable now is S, the arc length along the axis of the thread. So the variables are these geometrical variables here, the kinematic variables, the axial velocity and the spin about the axis, and the dynamical variables, the stress resultant and the bending and twisting moment vectors. So to go along with these variables, you have 17 governing equations, force balance, torque balance, geometric equations, and 4 constitutive relations. There are 2 unknown parameters in the problem, the coiling frequency, which is of primary interest here, and the filament length, the length from the nozzle down to the contact point, which is roughly equal to the fall height, but slightly greater, of course. So we need, therefore, 19 boundary conditions, and we get a 17th order geometrically nonlinear boundary value problem, which we can solve by a continuation method using this software here.
In this context, what does 17th order mean?
Oh, it means that you can write the set of differential equations as a set of coupled 17th first order equations for these variables.
Yes, okay.
For this software, you need to write the equations in a canonical form as a series of
I thought so,
first
but I
order.
was reluctant to believe it.
No, that's. So let's now look at some comparison with experimental observations. The experimental observations are at first sight very puzzling because they show radically different behaviors depending on the values of the flow rate and the viscosity. These show curves of the coiling frequency as a function of height in dimensional terms. So you see in some cases the frequency which decreases as a function of height. In other cases, a frequency which increases very rapidly as a function of height with a kind of a gap here where there are no observations. And then in yet other conditions, you see multiple states, these sorts of stair-step features, where you can have 2 or even 3 states that occur at the same value of the fall height and for the same value of the experimental parameters. So now what we do is we formulate our model, we put in the parameters of the fluid and hope for the best, and this is what we get. These are the predictions of the numerical model, and I emphasize there are no adjustable parameters. You get what you get. So that's very gratifying to get such a good agreement, but it's not yet a physical understanding of what's going on. So our next task was to try to develop that understanding by a more detailed examination of the equations.
Yeah, sorry.
Oh, I'm sorry.
There are 2 symbols on the right.
Oh, yes.
Squares and circles.
Yeah, I'm sorry, the squares and the circles, you mean? One of them is with height, let's see now, it would be the height increasing, due experiments with height increasing, and the other with the height decreasing. So you can see there was some hysteresis involved. Yeah.
And what's the reason of systematic deviation in the first panel of the experiment?
We don't know. There's about 20% off, and we're not sure. It gets the shape nicely, but the systematic deviation is definitely a feature. I think it might be due to the fact that in that case, the height, as you see, is very small, 1-2 centimeters. The thread in that case is quite thick. So I think the thin thread approximation that's built into the governing equations breaks down, and you have to take into account a higher order expansion for a thicker thread.
And quite what the initial condition at the top of the thread.
I'm sorry?
And what is the initial condition at the top of the thread as it comes out of the nozzle won't be lost in a short drop.
No, that's a good point. Yeah.
Numerically, when you find these multiple states,
Yeah.
how do you do that? Is that with, are they steady states?
Well, what you do is you use a continuation method. You start with a state which is an analytical solution of the equations but does not satisfy the boundary conditions. Then you gradually adjust those boundary conditions until you get the right ones and the solution adjusts to a steady state. Then you can take that solution and continue it. For example, I might have a state located down here or down here, and I continue that state by, say, increasing the fall height, and the code automatically carries me along this curve. And there's no time dependence involved in this problem or in this numerical procedure, so you can find these states even if they're not stable. And now what I'm going to show is the problem of stability. So we can look at the stability of these steady rotating states, carry out a linear stability analysis in terms of global modes. This gives you a 21st order system. And we can do the solution with the same numerical continuation method. And when we locate the unstable portions, we find this. So the unstable portions are the dashed ones. And my experimentalist colleagues were very good. They found observed states which are located on the stable portions of those, the different branches. So here is a summary to summarizes pretty much everything we've learned about basic liquid rope coiling. On the left, you have the same figure as before to indicate the important parameters. This diagram shows the dimensionless coiling frequency versus the dimensionless fall height for the parameters of one of our laboratory experiments. And so you see this red curve was calculated using the numerical model. The dashed portions are the unstable portions of the branch. First, going from the left forward, we have first what we call a viscous mode of coiling. I liken it to toothpaste, squeezed from a tube against a nearby surface. In that case, both gravity and inertia are negligible, and you only have viscous forces at play. And the scaling law for that frequency as a function of height is shown down here. Next, as you increase the fall height, you get what we call a gravitational mode of coiling. This has a rather complicated scaling law with a patented Cambridge logarithmic term found by Blount and Lister. And in that case, the viscous forces which resist bending in the coil are balanced by gravity. Then moving all the way to the top, to very high fall heights, we have this inertial mode of coiling in which the thin filament is nearly straight all the way down to you have this tiny little coil at the bottom. This is the scaling law for that type of coiling. And then the most interesting region comes last, or it's in the middle, is what we call inertial gravitational. What this is a resonant mode of coiling. What happens is that the coil at the bottom here fixes a frequency. If that frequency is close to one of the natural frequencies of oscillation of this long tail, this tail structure with a non-uniform distribution of mass, then the tail enters into resonance with the coil, and you get these large excursions that you saw in one of my previous movies. And so here you see the first three pendulum modes. The frequency is proportional in all cases to the standard simple pendulum frequency. But of course we have an infinite number of those modes since we have a continuous distribution of mass along the thread. And these pendulum modes correspond to these peaks or bumps in the curve. Those are just classical resonance peaks. So those are the four fundamental modes of coiling. But now I want to move to the new phenomenon that we see when we do experiments with lower viscosities. The ones I showed you previously were for viscosities about 100,000 times that of water. Now I'm going to show you experimental results from using viscosities roughly from 500 to 5,000 times water. So I'm calling that low viscosity, relatively speaking. So here's the experimental setup. In this case, gravity is the driving force for the we don't use a syringe pump. So this thread simply falls from a constant head reservoir onto a small platform here, and that's observed with a rapid camera. Everything now I'm going to show you happens in this little sort of 1 or 2 millimeter wide region at the on the top of the platform. So this shows one movie of multiple states of a viscous jet. Oops, sorry, that was stagnation point flow at the beginning, then coiling is another state. This is slowed down by a factor of 20. And then finally, you have the state of folding plus rotation. You notice that the width of the pile of fluid seems to increase and decrease in a periodic fashion. What's happening there is that the thread is essentially folding in a plane, and the plane of folding is itself rotating with a much lower frequency. So it's quite a complicated behavior. Now I want to show you a movie again with all of these three states in the same movie. What my colleagues did is simply to to give the apparatus a tap with their knuckles to create a finite amplitude perturbation, which causes a transition from one of these states to the next. So the movie starts with this folding plus rotation state here on the right. Looks like this. Then we tap the apparatus. It changes to coiling. Tap the apparatus again. And it changes to stagnation flow. So all of these three states are stable for the same values of the experimental parameters. The transitions occur if you just wait, but to see which states were observable for certain parameters, my colleagues did the tapping routine just to speed things up a bit. So now I want to talk about some remarkable states which I call liquid superbuckling. It's not a very lovely term, but it's a fluid mechanical analog of solid mechanical supercoiling. And you're all familiar with this very aggravating example of supercoiling here with telephone cords. I guess those don't much exist anymore. And DNA strands also undergo supercoiling, where you take a structure coiled at a small scale and coil it again at a larger scale. So here is an example of one that what we call periodic column collapse. You see a primary coiling instability forms a hollow column, which then collapses, undergoes its own secondary buckling instability. This one I like very much. We call this the supercoiling state. Here the hollow column formed by the primary coiling instability undergoes its own global secondary buckling instability with its own well-defined frequency. So here, just to be a bit more quantitative about that supercoiling state, it turns out that there are three frequencies. There is the primary coiling frequency, that's shown in red here. That's the frequency of the coiling up here. If you look here, the omega goes up to almost 20,000. That's about 2,000 turns per second. Some of these things are when you let the fluid fall from nearly a meter, you get these extremely rapid coiling instabilities. The secondary buckling is about a factor of 10 slower. That's this buckling that occurs here. And finally, there's a rotation of the buckling plane, which I call secondary rotation, which is down by another order of magnitude or two in frequency.
These are experiments. You don't have the theory for the secondary.
No. Unfortunately, the numerical model that we created is for stationary flow in a co-rotating frame. And we do have now a code, which I'll talk about, a code that can solve arbitrary time-dependent problems of viscous threads. But something this complicated with a meter fall height, it could never do it. So we're not there yet. Okay, well, here are some state diagrams to show which of these different states are observed as a function of the fall height, the flow rate, and two different viscosities. So the S is stagnation, F is folding, C is coiling, PC is periodic collapse, and SC is supercoiling. So the 5 different states that I showed you. And this is the phase diagram for those states. What you see is that in some places only a single state is observed. In other places you have 2 states which can be observed, and sometimes as many as 3 can be found. And these 2 diagrams look quite similar topologically. In fact, if you take this diagram and you shift it up and to the right, you get something that looks more like this diagram. So that suggests we need to do some dimensional analysis. So here it is. So we say that the height of a given boundary in the state diagram is some function of these physical parameters, the flow rate, the gravity, viscosity, density, and surface tension. We just use the standard pi theorem for this. We find 3 dimensionless groups. So it suggests that we ought to plot the dimensionless fall height as a function of the dimensionless flow rate for different values of this surface tension parameter. That should give us everything we need. And here are the results. The 2 values of the surface tension parameter corresponding to the 2 viscosities I showed before. And now you see that the two diagrams are much more similar to each other. They're not identical, as you would expect, given that these values are different, but they're still much closer to each other. So now what I'm going to try to show you is what controls the selection of these states. We're going to try to find a dimensionless parameter that governs the selection here. So the first order structure of the state diagrams is really twofold. This is for the viscosity of 3350 centistokes. The buckling states are shown in color, and in gray are shown the states in which no buckling occurs, the regions of the diagram with no buckling. So there's a region down here below this black line for small fall heights where there's no buckling because the height is too low. But there's also this region here to the right of the diagram where there's no buckling because the flow rate is too high. And now if you were to try to make water coil, you'd be out here somewhere. You can't get it to do it. So I'm going to look at this Q2 high region, see what we can learn from that. So let's consider the cessation of coiling along this branch, the Q2 high branch, in the inertial limit, that is for a fall height greater than 15 centimeters or so. Well, the idea is that coiling will stop when the non-penetration condition is violated. So from this diagram, you can see that if A cannot be greater than R, because otherwise the thread would intersect itself in the middle of the circle. So we do a simple scaling analysis. We take the fluid to be in free fall. We use the expression for R corresponding to inertial coiling, as found by Maharan. And we find then, by comparing these two, that R equals A when this dimensionless group is of order unity. So this seems to be the dimensionless group we're looking for, but in more physical terms, we expect this group to be related to the ratio of A, the thread radius, to R, the coiling radius. So indeed, that's what we find. This is from the numerical solutions. This just shows the relationship between that dimensionless parameter I introduced and the ratio A over R going up to 1, where it can't be any higher than that. So here it just shows you the definitions of these two parameters. And so you can think of this parameter as the wall thickness parameter. Right? If A over R is small, you've got a thin-walled cylinder. A over R large, you've got a thick-walled cylinder. So now we go back to our state diagrams and we lay down contours of this parameter A over R. This is the This is the dimensionless phase diagram, and you see these black lines are contours of constant values of A over R. Here's 1.0, 0.8, 0.6, 0.4, and as you can see, those contours look like they follow reasonably well the boundaries between these different colors in the state diagram. So what we can do is then, for the inertial regime, just simply make a plot versus A over R of the states that are observed, or the regions or the ranges of A over R over which the different states are observed. Again, stagnation flow, folding, coiling, supercoiling, and periodic collapse. We do that for our two viscosities. As you can see, the results are almost identical for the two. They're very reproducible. And you see the different fields overlap one another. So you can see, therefore, up to, for example, here you can see up to 3 states at a given value of A over R. Okay, I want to turn now to another lovely phenomenon we've heard about from Yves Coudert. This is not quite the same physics, but it's the phenomenon is similar. And that is spiral waves. Now you recall I mentioned earlier on in one of my movies that the coils were not being laid down directly on top of the previous coils that had already been laid down. Here's an example of that viewed obliquely. As you see, there's a kind of an offset as each coil is laid down on the previous one. So the center of coiling itself is moving along around a circle, which is distinct from the center of the coiling itself. So now you see also in this diagram lots of air bubbles, all these little white dots. So what that suggests is we ought to do the experiment on a transparent glass plate and look up from beneath, see what's happening. And what you find is spiral waves of bubbles. It's not a very long movie, I'm sorry for that. But the bubbles arrange themselves in a spiral pattern here with, in this case, 5 branches. We see other numbers of branches under different conditions, sometimes 4, sometimes only 3. But what's happening, it can be understood kinematically. What you have is bubbles being trapped. Let me go back one. Bubbles are being trapped as each coil gets laid down on top of the others. And by a mechanism we don't fully understand, bubbles are being trapped at that intersection point. And the location of that point of trapping slowly migrates around the circle. So what we have is a composition of 2 motions, the slow migration around the circle of the bubble trapping point and the subsequent radial advection of the bubbles in the fluid that's spreading over the plate. So we can ask what kind of spirals are being formed here. So the radial velocity of the bubble, this is simply using lubrication theory for the spreading of the fluid over the plate. And
Excuse me.
Yes.
Roughly how many bubbles are formed per perimeter, per one rotation?
That's a good question. I think it's typically just 1 or 2.
Okay.
So the radial velocity of the bubble at the top of this thin lubrication layer is given by this expression here. The depth of the pool can be calculated, and we just simply take that to be approximately the depth at the edge of the coiling filament. The angular velocity of the bubble trapping point is just moving steadily around the circle at an angular velocity omega. So from that we can figure that the radius of the bubble is proportional to theta minus theta naught to the 1/2 power, and that's a Fermat spiral. So that seems to be basically the spiral we're looking for within the assumptions involved in approximating this expression here. Okay, now I want to turn to the fluid mechanical sewing machine. There are people here who know as well as I do or better what this is. So this is the experimental setup. Instead of letting your filament fall on a rigid surface or a motionless surface, you let it fall on a moving belt. And the first pioneering experiments on this were done by Keith Moffat and I won't try to say the first name, Jong, here at Cambridge. More systematic experiments were later done by Sonny Chu Webster and John Lister, again here at Cambridge. And then with a very nicely engineered device by Stephen Morris at the University of Toronto. Well, this is just a quick overview of the remarkable patterns that are produced by this simple device. What you do is you look down, this is looking down from above on the shape of the viscous filament that's laid down on the belt. And you can see why it's called the fluid mechanical sewing machine. These resemble stitch patterns. So you see up here, the steady drag thread, of course, is just confined to a vertical plane. As the belt speed is reduced, you get a meandering state. And as the belt speed is reduced further, you get a whole zoological park of states, including biperiodic states, 2x2 alternating loops, one on the left, one on the right, and so forth, a W pattern, double coiling, semi-random, something like a dozen different patterns in all. This is a nice video from Stephen Morris showing the bifurcation, there we go, from the steady drag state to meandering. This happens as the belt speed here is being decreased just little by little. And when the belt speed reaches the speed at which the fluid is striking the belt, you get this first bifurcation to meandering. Here's the next movie is the bifurcation from meandering to alternating loops. So now the meandering has a larger amplitude. There it's starting to go. There are the alternating loops, one on the left, one on the right, one on the left, and so on. So as you continue, you see lots of other different bifurcations. I'll show you in a schematic view on the next slide.
What's the control parameter?
Oh, it's the belt speed.
Speed again.
The belt speed. What he's done is he's got a programmable belt speed where you can just diminish it little by little and watch the bifurcations occur. So here is a comparison of the experiments versus our numerical simulation. So the experiments are those of Morris that I've already shown you some. The simulation was done mostly by Pierre-Thomas Brun, who was a PhD student of mine working with me, and Basile Odoli, who developed a so-called discrete viscous rods algorithm, which is the first algorithm that's capable of simulating non-stationary behaviors of viscous threads. Within reason, as I said, there are some behaviors we can't get yet with this. So the experimental data are shown here with the same color scheme as the numerical simulations, which are shown larger here. And if the numerical simulations, for technical reasons, don't have surface tension included in them. So there's some difference between the absolute values of these parameters here. This goes to 1.8, this only goes to 1.5 or so. But you see the same topology of states, right here, blue, green, red, blue, green, red. The yellow is out here, flanked on both sides by gray, which is the random patterns. And a pink region down here, which corresponds to this double coiling. So the numerical simulations really do a quite creditable job of capturing the behavior we're seeing in the experiments, even though the absolute values of the parameters are not quite correct. So this is a study that Pierre-Thomas Brun did of sewing machine patterns in the inertia-free limit. These are the patterns you see: a straight drag thread, meanders, alternating loops, translated coiling, and in a very small proportion of the parameter space you see this so-called W pattern. Well, what Pierre-Thomas did was to say, this is a plot, first of all, of the belt speed as a function of fall height, both in dimensionless form. But Pierre-Thomas' insight was to say, well, the critical parameter is the ratio of the belt speed and the velocity of the thread as it impinges on the belt. So let's look at things in terms of that ratio. And when you do so, you find that the boundaries between these different states are all horizontal lines on the diagram. So that suggested to us that it would be nice to find a reduced order model to try to explain what's going on here. So here's the essence of the reduced model. It's a model with 3 degrees of freedom. The variables are, first of all, r and psi, which are the polar coordinates of the contact point. This is the contact point of the thread relative to the center of the nozzle. And these are the polar coordinates at that point. And finally, this angle theta here, which is the orientation of the thread's axis at the contact point. So we used only those 3 variables. These are the equations, the first order differential equations governing the evolution of those variables as a function of arc length along the path laid down by the filament. So these 2 equations simply describe the kinematics of the contact point motion. And this last equation is an expression for the curvature of the path, theta prime, where the function kappa is obtained by fitting to the discrete viscous rods predictions. So here are the results, the reduced model in green versus the discrete viscous rods model in gold. These are the orbits in the frame of the nozzle, but here, this is perhaps more useful to look at. So these are for different values of that ratio of the belt speed over the impingement speed of the jet. So for 4 different values. And you see that the reduced model does a very good job at capturing the shape and even the wavelength of the patterns. So as a function of this single parameter V over U sub C. So let me turn now, in the time I have left, to the other part of my talk, which is patterns due to elastic threads. And the 2 parts of this are analogous to the fluid mechanical parts I've already described. So we did some work, first of all, on elastic rope coiling, which we published back about 10 years ago. This is analogous to liquid rope coiling, but it's a somewhat simpler problem. The equation is not of as high an order because the thread or the rod is essentially inextensible. So we have as dimensionless parameters a fall height, a feed rate, U, and a coiling frequency, omega. So the coiling frequency is just like the one I used for the fluid case. The experimental setups were developed by my colleagues Mehdi Habibi and Daniel Bon. I think they're very nice. The first one uses regular cotton threads, which are wound on a spool, and that spool then feeds the thread down onto a surface at a fixed velocity. The next, to access all the different regimes of coiling, in this case, we needed a second setup, and my colleague Mehdi Habibi invented this one, where he uses a syringe pump filled with water and a thread of wet spaghetti. This is Iranian spaghetti, which they softened for something like 10 minutes, then measured its elastic properties, loaded it into the syringe pump, and with one squirt of the syringe pump, ejected the thread onto a surface where it coils. So, just to summarize, here's the phase diagram for elastic rope coiling. It turns out to be even more complex than the phase diagram for liquid rope coiling in one respect. So we have first at lower left, we have an elastic regime of coiling. This is for low fall heights, where the coiling rope, or the coiling rod, looks like this. So in that case, it's again gravity and inertia are both negligible. It's only the elastic forces that are in play, and so it looks like that. It's kind of forced or kinematic coiling. Next, we have a gravitational coiling, where gravity balances the elastic forces in this lowermost region of coiling. Then to move to the inertial region for large fall heights and large feed rates, this is what's called the whirling string mode. If you look in Love's book on elasticity, he talks about this. It's a mode where the string is whirling, but the string has no resistance to bending, or bending resistance is negligible. So you have a centrifugal acceleration balancing the gravitational force in the coil. And it looks like this. That's a typical shape of the filament in this region. Then finally, in the second inertial region is what are called whirling shaft modes. That's Love's terminology. And this again is a typical, oops, sorry, wrong one. There we go. So this is a typical shape of the filament in that regime. And that's basically standing elastic waves. Inertia is balanced by the resistance to bending. So here are the numerics versus the experiments. The numerics, of course, are the blue curves, and the experiments are the red dots. So again, we get a quite nice agreement between the predictions of the continuation method and the experimental observations. So let me turn last, this is my last slide, to the elastic sewing machine. We'll talk about the fluid mechanical sewing machine. We can do the same thing by letting an elastic thread fall onto a moving belt and see what patterns are formed there. And this is what it looks like. These are some of the patterns you see. Now in blue are the patterns you're already familiar with from the fluid mechanical problem. You have the meanders here, the straight drag thread, of course, biperiodic meanders, W pattern, alternating loops, what we call 2x2, where you have 2 loops to the left, 2 loops to the right, double coiling, and translated coiling. But in addition, there are new patterns that appear in the elastic case. This one, my colleagues call it an ampersand pattern. It looks like kind of like an ampersand on its side. And this is a very strange pattern, a 2x1 pattern, where you have 2 loops on the left, 1 on the right, 2 on the left, 1 on the right, and so on.
This is experiment.
Yes, this is laboratory experiments. We haven't tried to simulate this yet. There is a discrete viscous rods code that the same people developed, and so it should be possible to simulate them, but we haven't done that yet. So that's all I have to show you. I hope I've convinced you that a very, very simple system can give rise to an extraordinarily beautiful range of patterns. It's very gratifying to work on for that reason. Thank you.
Questions? Keith?
That was a wonderfully exciting talk. Thank you very much. You're right, it's an incredibly rich range of phenomena. There were just two comments that I would make. I think you mentioned the problem of bubble entrapment.
Yes, right.
Throwing them out in the spiral. I'm pretty sure that must be through cusps. If you take a frame rotating, as you did, a rotating frame, then you've got a steady flow in which there is a cusp present where the coil hits the...
Where two fibers...
Where they come together.
They come together, yeah,
And they're both moving, the boundary is moving.
Yes.
And pulling the air in. And it's got to be a cusp.
Let me
Thank you,
contradict
that's-
Moffat for the first time ever. It's completely wrong. I believe it's the central gas region, which forms a sort of cone,
That's right.
Which
That's
is-
called cone.
you know, not necessarily singular, but sharp at the bottom. And then because you've got flow across that, that's a classic situation, you know, in theories of Taylor and ever since in practical devices for making foams today, for giving you a train of monodispersed bubbles. Well-known phenomenon. And you can model that by initially assuming that the downward flow is rotationally symmetric, just the first approximation.
Yes, right.
Yeah. And that gives you your train of bubbles, and then the rotation that's actually there will then give you your spark.
How do the bubbles get out?
Everything gets out. The liquid disperses to the sides radially,
Yeah.
and the bubbles are entrained in it.
Well, there's two hypotheses.
Only one is right.
Well, both could be wrong.
What's the radial velocity in your case? What's the radial velocity?
I
Will
don't.
be at the
The
center.
velocity of the liquid, they're very
Which
small
is
bubbles,
very
so they're
small.
simply entrained, I would say, and they just radially.
But Keith had another comment, I believe.
Well, I did. The other one was you mentioned the very preliminary experiment that Jaitak Jung and I did
Yes, right.
with a moving substrate. And our aim actually was to try and determine the equation when it comes down on a straight line before
Yes, right.
bifurcation.
Right.
What is the equation of that curve
Mm.
that is drawn out? And we had an equation for that, but it wasn't right, I don't think. We thought it was an extremely difficult problem. I don't know, I think we had viscosity and surface tension and inertia, of course, and gravity. And it was all just too complicated, so
I see.
we never quite
I
solved it.
see, thank you.
But it's a nice problem. I don't know if anyone has solved that.
Well, Sonny Chu Webster and John Lister did a pure stretching solution, which can't satisfy all the boundary conditions. Where you have boundary layers at both the top, at the nozzle, and at the contact point due to the bending
Yeah.
forces. And that makes it complicated.
Yeah.
So you can't do it analytically. What we did is to solve that numerically using the same software I pointed out. And then we did a stability analysis on that to determine the bifurcation to meandering. But yes, you're right. It's the shape of the thing is too complicated to do analytically.
Jane?
Are you able to track the twisting degree of freedom? As wondering how would that vary?
Oh, yes, okay.
Leading to these different patterns.
In the numerical solutions, everything is there for your inspection. So you can determine, for example, what we calculated was the rate of viscous dissipation due to stretching, to bending, and to twisting as functions of arc length along the axis. And the twisting turns out to be quite important in the coil. It's not important in the tail. But asymptotically, as the thread gets very, very long and stretched, the twisting becomes small relative to bending. And it's bending dissipation that dominates in the coil. So that's what we found.
But also just somehow intuitively you would think the translational coiling would involve very little twisting, but the ones that twist, bend, turn, switch the coiling might have something to do with the amount of twisting.
Yes, that's you may be right. It was harder to do the calculation for the discrete viscous rods model, but they did some calculations of twisting dissipation. I confess I forget what the results were for all these different patterns.
Can you say something about the numerical model?
Oh, sure.
How it works?
Sure. Well, it's not software that we wrote. It's freely available software called awhole, and it's a package for bifurcation analysis and solution of coupled ordinary ODEs. So what you do to get a solution for this very high order system is you start with a simple analytical solution. It was a quarter circle, so something coming out of a nozzle and then going down to be parallel to the plate. That solution you can write down analytically, but it doesn't satisfy all the boundary conditions you want. So what you do is you take your boundary conditions and you add to them continuation parameters. So a parameter it ranges from 0 to 1, say, and 0 corresponds to the boundary conditions actually satisfied by your analytical solution, and 1 would correspond to the true boundary conditions that you want to get to.
Yeah.
So you start with
That's solving the differential equations. Yeah. I was
That's right.
thinking more. How do you get? Is that how you get patterns like this as well?
Oh, well, these, as I say, we didn't do numerically.
Yeah,
But
but
the fluid
similar ones.
the
yes.
similar ones from the fluid
Yes,
dynamical
yes.
sewing machine. Yeah, that's a discrete viscous rods model. It's called. Now I didn't develop this, so I'm not the expert. But it's based on concepts from discrete differential geometry. In other words, you don't start by writing your equations out in their full continuum form, but you start by describing your filament. Is there chalk?
Yes.
Your filament is simply a simple model like this with nodes and edges connecting them. So you start from the very beginning with a model like that and derive all the conservation equations in that framework. And it turns out to be very robust numerically, and that's how they were able to do the calculations for the time-dependent patterns.
Can you say again what that's called, the model?
Discrete viscous rods.
Rods, okay. Thank you.
And they have a discrete elastic rods code as well, but we didn't use that one.
Any other questions? I have a question. For this transition between different patterns of the falling, let's say, viscous thread, is there any way to understand by some scaling law when the transitions happen as a function of the ratio of the two velocities?
Well, what we did on that, I made up is this going to come back on? Yes. So from the one thing you can do, maybe in the direction of answering your question, is to look at the bifurcations that occur in that simple 3 degree of freedom model.
Aha.
And what we get there, this is the, oops. Again, this is not something I did. This was Tom Eves and John Lister who did this part. But this shows the transitions among the states. So this is the translated coiling state. This is the alternating loops state. This is the W pattern up here. And this is the meanders. And you find hysteresis as you compared to belt speed increasing, belt speed decreasing. But this shows the bifurcations. The nature of the bifurcations that occur in each case is a fold point, period doubling, and torus bifurcation. And those occur, if you compare this and this, you see that they occur at roughly the same values of this ratio V over UC. It's not a perfect agreement, but we capture all the basic behavior, including the fact that the W pattern is skipped when the belt speed decreases.
It must depend on viscosity, no?
Well, the viscosity is all
I see,
locked in this parameter
I see.
here. The U sub C is so to speak the free fall speed of the thread, taking into account viscous forces. So in a sense, the whole model abstracts from viscosity and all physical properties of the fluid. Once you express it in terms of this ratio, that's the only parameter that matters.
Could I end with a facetious comment?
Sure.
Would I be deluded in thinking that there is no future for these experiments in the University of Nairobi because it's on the equator? Does the Coriolis force?
No, in fact, these are too small. These are far too small to be affected by the rotation of the Earth.
The Coriolis is the rotating.
It's nothing to do with the rotation.
No, the rotating frame here is the one you put yourself in, the one that rotates with the contact point.
Okay.
That's the rotating frame. It's not the Earth's rotation.
This is like the bathtub problem, you know, that some people think that the world, as you empty your bathtub, is in opposite direction on north hemisphere and south hemisphere, but it's not true.
Okay, I get it.
Yeah. John, you have any comments or questions?
It is true if you do the careful experiment. The careful experiment is remarkably careful.
It doesn't involve a human in the bath.
That's
So the human gets out, they keep the bath and leave enough water sitting there.
Exactly.
So you can't do that. You can't pull the plug out because it meanders electrochemically dissolved. And you need to have an amplification of 10 to the 5 or something of the rotation of the Earth to what you can see, which requires an enormous stretch. So you need several meters of tank and millimeter hole to drain. And then it works.
We recommend that our first year students watch the video as to how careful it has to be, having screwed up the question on their example sheets.
All right. If no other comments, facetious or otherwise, let's thank the speaker again.
Well done.